Hi, and welcome to Pharmacology of the Synapse. In this video, we will take a closer look at the synaptic changes that occur in Fragile X syndrome. As we saw in the previous video, Fragile X syndrome is caused by loss of the FMRP protein, or Fragile X mental retardation protein. FMRP is a negative regulator of translation, which is the step where RNA is converted to protein. FMRP regulates a lot of brain mRNAs, around 4%, and many of these mRNAs are important for synapse development and neuronal plasticity. Loss of the FMRP protein causes many changes to neurons in addition to the increased immature dendrites, such as increased oxidative stress and channelopathies, which is a term used to describe aberrant function of ion channels like calcium channels and potassium channels. One major hypothesis about the synaptic aberrations seen in Fragile X syndrome is the glutamatergic hypothesis. In Fragile X syndrome, there is an increase in metabotropic glutamate receptor signaling and decreases in GABA and dopaminergic signaling. Let's go over what mGluR receptors are and what happens if there is too much mGluR signaling. mGluRs are G-protein coupled receptors. This figure shows the G-protein signaling cycle that occurs with GPCRs. mGluR1 and 5 are GQ coupled receptors. When activated by agonists, they activate phospholipase C and other intracellular pathways. Activation of mGluR5 receptors and activation of GQ signaling cascades causes downstream protein synthesis. You don't need to remember all the steps in the signaling cascade or what proteins get synthesized. The protein synthesis causes internalization of AMPA receptors from the surface. AMPA receptors are the fast ionotropic glutamate receptors that mediate a lot of neuronal transmission. Loss of these AMPA receptors from the synapses will dampen synaptic transmission, called long-term depression. Here is another schematic that illustrates the glutamatergic hypothesis of Fragile X syndrome. On the left panel, FMRP normally acts as a transcriptional repressor to repress protein synthesis and keep AMPA internalization in check. When FMRP is missing, protein synthesis is uncontrolled, and this accelerates the internalization of AMPA receptors, leading to long-term depression of the synapse and less synaptic activity. As a response to the dampened synaptic activity and long-term depression, it is hypothesized that there may be an increase in the production of dendritic spines and growth of new synapses by the neuron to try and compensate for the decreased synaptic transmission. This compensatory production of dendritic spines causes this increase in immature spine numbers seen in Fragile X syndrome.